Before we get into the technical details, we're going to start off with a story. 2 months ago, someone identified a GitHub Actions misconfiguration in a public repository owned by one of the largest domestic chip manufacturers in the United States. Anyone with a GitHub account could have exploited it simply by creating a pull request. The vulnerability allowed them to escalate to enterprise admin privileges over that company's GitHub Enterprise Cloud tenant. This provided access to some of that company's most sensitive intellectual property. They had the privileges to make every single repository public or even delete their GitHub organizations entirely, which would trigger an immediate loss of over 120,000 repositories. Thankfully, it was not an APT. It was me. And I disclosed the vulnerability to the company, and they were able to fix it.
Before we get started, we read online that as long as we have a disclaimer, nobody is allowed to sue us. So here we go. All vulnerabilities mentioned during this talk have been remediated. The views and opinions expressed are solely our own. And this content is not endorsed by, nor does it represent the views of our employers. All right. Should be good to go. Adnan, go ahead and introduce yourself.
All right. My name is Adnan Khan. For my day job, I work as a security engineer. But on the side, I'm a security researcher and a bug bounty hunter. And I live in the wonderful city of Baltimore, Maryland.
My name is John Stawinski. I'm a red team security engineer. I also perform CI/CD research. In a past life, I was a collegiate wrestler. And I work remote and get to move around a lot and see some cool places. Let's start by talking about why we're here. We are here because we use a systemic vulnerability class to hack a lot of organizations, including but not limited to the ones you see on screen. In most of these organizations, we had enough access to cause a full-scale supply chain attack similar to SolarWinds. Everybody has heard of SolarWinds, and we all know that supply chain attacks are on the rise. But what not everyone knows is that attackers are starting to focus on a new entry point for these supply chain attacks, namely public GitHub repositories. Based on our experience, public GitHub repos are one of the quickest and easiest ways for an attacker to launch a full-scale supply chain attack.
All right, John. We all know that sometimes news outlets can be a bit dramatic. Is this issue really that bad?
Yes, it is. What we're going to show you today is there's a systemic lack of awareness around self-hosted CI/CD agent security in the world's most advanced technological organizations, and it's exposing them to critical supply chain attacks.
Through 3 case studies covering exploits that we conducted through our research, we're going to show you how the tech community doesn't know enough about these attacks. Some of these attacks are very easy to pull off, and some of these attacks could even change the economic balance of power in the world. So how do we start here? Well, it all started back in August of 2022 when myself and colleagues at my former employer on a red team got access to one of the client networks after obtaining a GitHub token and using a self-hosted runner that we were able to take advantage of to get back into the network. That led to a talk at ShmooCon called Phantom of the Pipeline and the associated release of the first version of the tool, Gato, for automating self-hosted runner discovery.
Around the time that Adnan, Mason Davis, and Matt Chakosky were developing Gato, I joined them on the red team. And Gato was my entry to CI/CD security. So I started using Gato to discover and exploit GitHub Actions vulnerabilities, mostly on these internal red team engagements. And then we were just seeing it so much that we started looking into it more and more. And we dove deeper into GitHub Actions post-exploitation. And then Adnan had an idea that took it to the next level.
There was a little asterisk at the end of the ShmooCon presentation that kind of mentioned if you were to fix a typo on a public repository and then modify the workflow file in your fork and create a pull request, you could get access to that self-hosted runner attached to it and persist on it for further attacks. This led to a vulnerability disclosure to the GitHub Actions runner images repository that was accepted as a critical report and could have allowed an attacker to conduct a supply chain attack on almost every GitHub customer that uses hosted runner images.
We decided to start searching the internet for more of these misconfigurations. And we ended up realizing that they were kind of everywhere. So we teamed up and kind of went on a vulnerability research campaign on the side. And we ended up finding these misconfigurations that could lead to supply chain attacks in public repositories all over the board.
Before we go into the interesting information about the attacks, I want to make sure everyone understands different types of GitHub runners. First, you have GitHub hosted runners. These are built by GitHub, updated frequently, and as of writing, cover a wide variety of operating systems and architectures. The key point with these GitHub hosted runners is that they are always ephemeral. When the workflow concludes, the runner is torn down.
Self-hosted runners, on the flip side, are dangerous. That's why we have the skull there. Self-hosted runners are not managed by GitHub. They're managed by end users. They run the Actions runner agent. That's how they actually execute GitHub Actions workflows. And security is solely the responsibility of the end user. And anyone who's done offensive security knows that end users are inherently insecure. The path of least resistance, so the area we focused a lot on during our research, the most insecure configuration, is a non-ephemeral self-hosted runner. So ephemeral self-hosted runners spin up and down for every workflow using a fresh container or VM or whatever. And non-ephemeral self-hosted runners live and they execute multiple workflows during their lifetime. This is what we focused on during our research. GitHub does warn their users about attaching self-hosted runners to public repositories, but the documentation's kind of hidden. So on the next slide, I'm going to show you what it looks like to register a self-hosted runner and attach it to your repository, and looking for documentation as we go. So I have my Black Hat is Cool repository. I'm going to runners, and then I'm looking at their documentation before I actually do anything. So I click on this link. I search through these other links. I don't see anything about security. I click on this other link, and we get a lot of info on self-hosted runners. It talks about requirements for self-hosted runner machines, usage limits, security, not yet, architecture, still no security, API endpoints that the runners use. And then down here near the bottom, it talks about self-hosted runner security. So GitHub says they recommend you only use self-hosted runners with private repositories. They also have other documentation out there explaining this in more detail. But the point we want to get across here is it's not obvious. These warnings should be very much in your face because of the risks that they can expose an organization to. And so if some dev is just going and attaching a self-hosted runner to a repo, they're probably not going to stumble across this information. When we teamed up, the first step was identifying self-hosted runners on public repos at scale. And to do that, we used workflow run log analysis.
So this slide captures some metrics taken back in the beginning of July on how many public repositories right now use either ephemeral or non-ephemeral self-hosted runners. So this number has gone down a bit since we first started our research. This is due in part to GitHub releasing a broader assortment of hosted runners, such as Mac M1 runners, where previously organizations had to have a self-hosted runner if they wanted to run integration tests on, say, an M1 Mac. For non-ephemeral runners, there are some, for ephemeral runners, there are some also interesting attack paths like Kubernetes and cloud privilege escalations techniques that could apply that also could lead to compromise. So it's not all safe just attaching these runners. Well, let's talk about workflow run log analysis. Every GitHub Actions workflow has a build log. This contains a lot of output on what happens in the build and a lot of contextual information that might not be present when you're just looking at the log in the user interface. When a GitHub repository has a self-hosted runner, there's additional information that someone can gain from that workflow. So if an attacker wants to conduct an attack against a public repository, by looking at the run log, they can learn about how it's configured and have everything they need to plan an attack before they conduct a single malicious action. And it's important to remember here, anyone with a GitHub account is able to download the run log from a public repository using the API or the web interface. Here's a sample workflow log taken from a Google-owned repository. This one is not vulnerable anymore. However, I'm going to walk through the interesting information that you can learn from this run log. First, you can look at the labels that are attached to that associated with that self-hosted runner. Using this, someone can figure out some of the context that runner is used in. Additionally, you'll be able to learn whether the runner is attached to the organization level, which can have some interesting privilege escalation techniques and lateral movement paths if there's sharing between public and private repositories for that self-hosted runner group. You can also learn then if it's at the repository level. Finally, you can learn about the machine name and the actual name of the runner group, all just by looking at the workflow run log. Next, you can learn about the GitHub token permissions used by subsequent workflows that run on that runner. So if someone gets on the runner from a fork, which has a read-only token, and the next one has a write token, well, they can get access to a write token by persisting. Next, using a somewhat clever heuristic, someone can determine whether the self-hosted runner is ephemeral or non-ephemeral by looking at the output of the actions checkout reusable action. If there's a step that says cleaning the repository, that means that it's cleaning out the previous checkout, which almost always means it's a non-ephemeral runner. And finally, by using contextual information in the run log, you can determine if it's running on an x84 or ARM64 architecture, and that can inform the payload you'll end up using. All right, John, let's show everyone how we can hack the planet.
Yeah, so a lot of orgs were using self-hosted runners on public repos. We've established that, but why does using self-hosted runners expose these orgs to compromise? There's a few reasons. The first is that people tend to use default settings, no matter how insecure. And in the case of public GitHub repos, some of their default settings are pretty insecure. The second is that becoming a contributor is not a security boundary. So all a contributor means is you've submitted a PR and it's gotten merged. That is not an actual security boundary. The third one is that anyone, even us, even you, can fix a typo.
All right, so what is this vulnerability? This vulnerability presents itself in the worst form when three things that, when by themselves could be considered best practices, come together. First, you have the default workflow approval requirement. For public GitHub repositories, workflows that run on the pull request trigger do not require approval to run if the user is a previous contributor. This simply means that if they've had a pull request approved and merged, it could be as small as a single character typo fix. Next, the repository has to have access to a non-ephemeral self-hosted runner. This means that the runner is not destroyed after the conclusion of the workflow. This is what creates the opportunity for inter-build interactions. So when you have this, someone who creates a fork PR can modify the workflow file in their fork and then run arbitrary code on that runner. The final step here is that subsequent workflows that also use the self-hosted runner have either an over-permissive GitHub token or use GitHub Actions workflow secrets that have access to other resources where you can move laterally to. When all of these things come together, you can have a major incident that will ruin your day.
We broke in our common attack path down into 3 steps for you guys. Step 1 is become a contributor. Step 2 is persist on the runner. So we'll install our run on runner C2 on their self-hosted GitHub runners. And then step 3, following these nice diagrams, is capturing secrets and moving laterally. This is the most important step. It's where we spent most of our time during our research. This is how you take trivial runner RCE and turn it into a complete supply chain compromise. We mentioned this earlier, but we are going to cover 3 case studies during this talk. They're each real live exploits. And during these case studies, we're going to use each one of them to illustrate a unique point about self-hosted runner security and how an attacker can abuse them. The first case study, we're going to show that the tech community is uninformed of these attacks that can have critical, widespread impact.
For the first case study, I'm going to talk about the vulnerability I submitted to GitHub on hacking GitHub through actions. This targeted the GitHub action runner images repository, which holds the code used to build GitHub-hosted runners. This is the attack that started everything. The first step here was to become a contributor. This involved fixing a typo. Shortly after, the pull request was approved by the maintainers and merged in.
It doesn't get much easier than that to cross a security boundary.
After establishing contributor status, the next step was planning the attack. The repository used nightly workflows for continuous integration. This had a GitHub token with all the write access. These integration tests ran on non-ephemeral self-hosted runners, and by observing how the workflows ran on the build logs, it was possible to determine that these images were saved off to either vCenter or Azure, and the workflow had secrets to both. So it was clear what I could get out of this. The mission here started to come together. So I'd have one shot to pull it off, because if I wasn't able to get access, I probably wouldn't be able to prove impact properly. with this, there was a window of time between implanting the runner and being able to access the GitHub token from that subsequent workflow in order to clean up the evidence of the implantation. So there was an element of timing that was quite critical here. The initial implantation had to be right before that scheduled run, so as soon as I got access, I could get that token and then clean up after myself. So go time was set. It was Friday, July 21st, 2023, and let me tell you, I was extremely nervous clicking that create draft pull request button right there. So the payload that I used for this was a modified linter.yaml file. The first thing you can see here is that I modified it to run as a matrix job. So I essentially have it run 6 payloads, 3 on one runner class, 3 on another. So because I wanted to make sure that when the subsequent workflow ran, I was on the runner it was running on. The next step was modifying a script that was checked out from the repository that called out to a second stage payload in a GIST. So just called it and piped it to bash to get arbitrary executions in a way that I could clean up after running it. This is the payload that it pulled down. It's a bash script that installs a runner on runner. So the first thing it does is it decodes a hard-coded access token, which it uses to pull down a self-hosted runner registration token. Next, it extracts it. It downloads the actions runner binary from GitHub and extracts it. Finally, it configures it to connect to a command and control repository and then runs it. It's important to note here the runner tracking ID. When that environment variable is set to 0, it informs the GitHub Actions runner to not reap orphan processes at the conclusion of the workflow. So when the initial implantation workflow concludes, my persistence mechanism lives on. So here you can see the subsequent workflows are running and my implantation workflow right below it. So what does persisting on this self-hosted runner provide? Well, with a GitHub token that has actions right, it's possible to delete the workflow run logs with the GitHub API. With access to unredacted scripts on the file system, that can provide access to secrets. And internal network access provides lateral movement opportunities. With a GitHub token that has contents right access, it's possible to issue a dispatch event to trigger other workflows, which leads to pipeline privilege escalation. And finally, this is like that SolarWinds style. Interacting with ongoing builds can lead to general supply chain compromise. After I saw the runners check into my C2 repository.
If anyone's familiar with C2, this almost looks like a C2 panel, right? So this is our own GitHub repository, and it's all of our self-hosted runners just checking in. And what's great about this is you can just make a little web shell workflow, and then you can use the workflow dispatch to execute commands directly on your self-hosted runners, and it operates just like a web shell. So it's a great way to gain and use code execution.
So I was able to use the GitHub token here with that actions right access to clear the test workflows.
At this point, it's like the attack never happened if you're looking at the repository.
With internal network access, lateral. So with the web shell, it's possible to exfiltrate secrets. So one of the more simple ways is simply to take that script that's on the runner's file system, base64 encode it, and print it to the run log of the private repository. And if there's larger files that you want to exfiltrate, you can use the actions the actions upload artifact reusable action to pull off larger files of that could be multiple gigabytes in size. And finally, for more complex cases, such as if the subsequent workflow only runs, say, once a month, you can place a script in the git hooks directory of the original checkout repository, and that'll trigger payload execution upon the next workflow run. With access to the internal network, you can move laterally. Here, in this case, I had secrets to vCenter as the administrator, so if I had set up a traffic channel, it's likely that I would have been able to log in as admin.
Another potential impact is build tampering. So when a legitimate build starts, the runner that we now control checks out code. And then what you can do is you can just swap build scripts during runtime. So you can add your own malicious code to this build script. And what will happen is any artifacts produced from that build will now be poisoned. They'll have your own malicious code. And anyone who downloads these artifacts or uses them will be executing your own code.
So I want to talk about pipeline privilege escalation here. So this is one way someone could have gotten code into the main branch of the repository. There's another workflow in this repository that ran on repository dispatch. That just requires that contents write permission to trigger. Next, you can see this repository uses input from that dispatch event within a run step. This means if someone simply altered the dispatch payload to contain shellcode, then they can get arbitrary code execution in that workflow. And finally, you can see that that workflow uses a secret that is most likely a GitHub access token belonging to a GitHub employee, because that's how it's used in the workflow to approve and merge pull requests. So if an attacker gains access to that, they can approve and merge their own pull requests into the main branch of this repository.
So what is the final impact here with the supply chain compromise?
So if an attacker can modify code in the main branch, then all they have to do is wait until the next production release of the runner image to be able to attack GitHub's customers that use actions. In this case, they had a very rapid release cadence. So an attacker would only have to have their payload hide in plain sight for not a very long time. And if successful, they would be able to conduct a supply chain attack that impacts virtually every GitHub customer that uses actions. So let's recap what happened. Simply by becoming a contributor, it was possible to conduct a series of operations to get secrets, move laterally, and potentially even conduct an attack that impacts every single GitHub customer. So let's move on to case study 2. John, can you show how easy these attacks can be?
Yeah, so that last attack, it required fairly advanced CI/CD knowledge to exploit, right? So it's not something that the opportunistic attacker could do in an average day. This next case study is extremely easy. So we're going to talk about how we breached Microsoft's perimeter by abusing GitHub Actions misconfigurations in Microsoft DeepSpeed. To breach Microsoft's perimeter, back when we executed this attack, you didn't need to do any sort of social engineering, no picking up the phone. You didn't need to exploit a web application vulnerability. All you had to do was fix a typo. And by fix a typo, we mean become a contributor. Before we get into this attack, we want to touch on a trend that we've seen in AI/ML. So a lot of our targets have happened to be AI/ML repositories, and there's a few reasons for this. The first is these repositories need a lot of compute requirements for their builds and their tests. And so GitHub hosted runners, they don't have massive compute requirements, so these AI/ML repos are just taking self-hosted runners to do the job for them. Another thing we've all seen is engineers working on AI projects, they are under a lot of pressure. It's a race right now, and so they're moving as fast as they possibly can. And what we see is that developers are taking shortcuts at the expense of security. Microsoft DeepSpeed, for anyone who's not familiar, it's an open source deep learning optimization library. If you don't know what that means, don't worry. I also don't know what it means, and it's completely irrelevant for this attack. What is relevant is DeepSpeed is very popular, and if you look closely at this workflow file, you can see that the repository, surprise, surprise, uses self-hosted runners. So as soon as we saw this repo is using self-hosted runners, Adnan and I did what every good hacker should do. We picked up the phone and we called the grammar police. The grammar police, me and Adnan, showed up, and we ran their markdown files through Grammarly, and we found this tricky typo here. And so we removed the and submitted a pull request, and then a week later it was merged. So again, actually finding a typo, that is totally irrelevant. The reason we do this is because it's the easiest way to become a contributor without making a substantial development effort. So we fix a typo, then we're a contributor, and now if they're using default workflow approval requirements, we can execute code on their self-hosted runners. Our payload for DeepSpeed was a lot simpler. So we were looking through the workflow logs, and there wasn't too much opportunity for post-exploitation. So the GitHub tokens privileges were pretty restricted. There weren't a ton of GitHub secrets. So rather than full-on install our runner on runner C2, we just wanted to execute a few shell commands and see what we were working with. So this was our workflow and our fork, and we specified it to run on their self-hosted runners, and we just executed whoami, pwd, and ls. So again, very simple. Anyone in this room could have gone and done this. And the command output was pretty surprising. So if anyone's familiar with Active Directory, this output showed that the self-hosted runner was actually joined to Microsoft's Redmond domain. As far as I know, Redmond is one of Microsoft's largest and oldest domains. I think it was created in 1999. And what's worse is we now had code execution in the context of a senior developer working at Microsoft. So this was definitely a surprise when we looked at the build output. And like, we've worked on a red team together. What do you think someone could do with a foothold with the privileges of a senior developer?
Oh, well, I'm sure there's a lot to unpack there, but I'm almost certain that there's some people in this room that could do some terrible things with that access.
The whole point of this case study, again, is this wasn't a way to cause a supply chain attack. So the impact of these attacks can vary based on how everything's set up. But it was really easy to use these misconfigurations to breach Microsoft's perimeter. In some cases, to exploit self-hosted runners, you need advanced CI/CD knowledge. But in other cases, all you need is a typo fix and a few shell commands.
All right, now we're going to take a quick step back here and quickly demo Gato-x, a tool that actually automates the entire self-hosted runner takeover process, provided you can just fix a typo. So let's show a quick video of it. It's also available on GitHub right now. So here, I'm enumerating a repository, and I've learned that it has a non-ephemeral self-hosted runner. Now I'm just going to go ahead and fix the typo. So I create a pull request here with a typo fix that go through. And after making the pull request, I'm just going to jump ahead to it getting merged. So now it's merged in, and my user is a contributor. So after having the pull request merged in, I'm going to go ahead and just delete the fork, because Gato-x will make a new fork as part of the implementation payload. So go ahead and delete the fork real quick, and now switch over to using Gato-x. So I run it. What it does is it sets up the payload and the GIS file to deliver it, and then it's going to ask for confirmation. Just want to make sure user actually wants to go through with an overt attack. So after confirming the attack, Gato-x creates a draft pull request to deliver the payload. And here it's going through because their approval is not required because the default settings are in place. So now it's going to pull for that runner connecting back. And as soon as it connects, it's going to drop to a shell-like prompt. And I'm just going to run uname-a. So after I run this, what's happening in the back end is that Gato-x is issuing a workflow dispatch event to the command and control repository to execute code on that self-hosted runner. So there it calls back, and that's the result. So you can do a lot more with it. There's more features, well documented online.
Yeah, Gato-x really would save everyone a lot of time where we spent manually typing all of our payloads in. Gato-x automates all of that. OK, final case study. This has not been released in public before. I personally wasn't involved in this attack, so I'll take a step back, and I will let Adnan walk you through case study number 3.
All right. So the case study number 3 maps to that story that I started off with before, how these attacks could potentially change the economic balance of power in the world if threat actors were to gain extremely sensitive intellectual property of a major chip manufacturer. Third case study, we talk about how I was able to get inside Intel through a pull request and a couple of other extra steps. So before we go into the technical details of this case study, I want to talk about how GitHub features Intel within their enterprise customer success stories page. GitHub quotes the lead of Intel's OneSource team as stating that when they moved their code base to GitHub, they broke down barriers. Unfortunately, as you're probably going to see here, some of those barriers ended up being security. Unlike the previous case studies, this didn't start off with a typo fix. This started off with a phone request vulnerability in a small repository called AI containers within Intel's open source GitHub organization. There's a lot to that vulnerability, and we're not going to cover it here, but you don't really need to understand it to see what happens next. The key thing here is that it allowed someone to run arbitrary code in the context of a privileged workflow, which is how this starts off. So it checks out code, and then it runs it from the fork. How does it run it? Well, in this case, the workflow calls the tox module of Python, which uses the tox.ini file. So an attacker could simply either modify the tox.ini file or modify one of the unit tests called by that file to gain arbitrary code execution. The workflow also used a secret called action token within the same job. This means that someone, after getting arbitrary code execution, could get access to that token. That action token turned out to be a GitHub personal access token owned by an Intel employee. Now, if you see, if this picture looks familiar to you, it's because it's the same picture from before. It's another case of vulnerabilities arising within the general AI/ML space. So the first situation here is that there was an overly scoped access token attached to that repository as an action secret. Next, there was another non-ephemeral self-hosted runner attached to the public repository. That wasn't the one running the fork pull request workflows, but combined with the token, it was possible to get access to it. And finally, it's very likely that the changes to the workflows that introduced this vulnerability in the first place didn't really go through security reviews. So what could a single pull request do? Well, by creating a pull request, an attacker can get access to that action token. Now, the paths from this kind of branch off. On one hand, you have access to that non-ephemeral self-hosted runner, because an attacker can create a fork pull request and then use that token to approve the pull request, so that bypassing the entire typo fix step. And also, at that point, it doesn't matter what the approval requirements are. Next, that token also was SAML SSO authorized and as such had access to Intel's internal organizations. So when those two things came together, it allows enumerating those internal organizations, because the non-ephemeral self-hosted runner also egressed from Intel's North America corporate proxy, which allowed getting past the IP allow listing restriction that Intel had for their inner source repository. All of this allowed searching for internal misconfigurations. And in the bottom of the slide, you can see running Gato-x on Intel inner source with that token from their self-hosted runner. All right, all of this isn't great, but it's one employee and the runners and the DMZ. Shouldn't be a lot more to this, right? Well, there was an internal misconfiguration within a repository called inventory, which was used for a couple things in CI/CD infrastructure automation and just automating DevOps processes. So don't want to go into it too much. But the key thing here was that every Intel Blue Badge employee had write access to this repository. And in GitHub Actions, if you have write access to a repository, you have access to all of the secrets. That's just how GitHub Actions secrets work. To mitigate this, this repository had a rule set that prevented creating any new branches and modifying files on them. So it would prevent someone with write access from actually modifying workflows to get secrets. However, there was an exception to this rule set, which was that any branches matching the pattern gh-read-only-q/anything would not be subject to that rule. So if you just created a branch matching that pattern, you can get access to secrets. One of the interesting secrets on this repository was a conf GitHub token. This was used in another automation workflow, but the operation it performed suggested that it was likely to be an organization admin. Turns out it was. So this bot token belonged to the GitHub OneSource user under that Intel's enterprise tenant and was an enterprise admin of Intel's organizations, and as such, an organization admin to all of them. So it was possible here to run Gato-x to enumerate Intel's Intel restricted organization, which holds more of their highly sensitive intellectual property and is more restricted from the general Intel employee population. This access was unprecedented. Because the bot user was an org admin, simply to Intel restricted, it had admin access to all 16,000 plus repositories within that organization. A lot of the repositories within that organization were highly sensitive Intel top secret code or source code under strict NDAs with third parties. This access also would have allowed someone to make all of the repositories within Intel restricted public, and then everyone could access them. Or if someone just wanted to cause damage, they could issue a single delete API call and just delete the organization. This would cause a cascade of effects, with all the repositories being lost, yes, it's likely that with the help of GitHub support, they could be restored, but the loss of integrations and loss of developer productivity would cost a lot of money. Some of this source code that it had access to was highly sensitive. Here, this is a repository holding the intellectual property and chip designs for Intel's upcoming Royal Core x86 architecture. So this is definitely not something you'd want to get in the hands of an unauthorized actor. I want to take a step back and talk about personal access tokens and access control in general. This really isn't an isolated case with one employee over-provisioning a token. Because of the access to the organizations, I was able to get some interesting metrics. So 32% of the active personal access tokens to Intel restrictor and Intel inner source had 10 or more scopes checked. 79% of these didn't even have an expiration date at all, so they would be valid until that employee leaves. And finally, when enumerating organizations with a tool like Gato-x that you just mostly issues GET requests, this generates 0 audit log events, with the exception of organizations that might use GitHub's REST event logging beta, but developing detections off of that is extremely difficult.
Zooming out for a second, the 3 case studies we showed today, they're just a small example of our overall research. Honestly, we could have swapped in any number of case studies to show any number of unique points. We chose these because they illustrate stuff that we wanted to convey to everyone here. But at the end of our 8 months of research, we'd submitted over 20 reports to major players in the AI/ML, blockchain, and tech industry. As we started releasing our research, we were pleasantly surprised with the community's reaction. So directors of prominent organizations out there were reaching out to us to continue the conversation. And this showed us that these orgs do care about improving their CI/CD attack surface. They just didn't always know how. And so we're going to spend the last few minutes today showing everyone how you can protect your organization from risk.
So one of the easiest things you can do for public repositories that use self-hosted runners is to simply use the more restrictive approval setting.
Another thing you should always do is use manage ephemeral runners whenever possible. Remember, self-hosted runners are dangerous.
When using Git access tokens, try to use fine-grained tokens wherever possible.
Limit GitHub token permissions. They should only have read access unless absolutely necessary.
When using sensitive production deployment secrets for workflows, try to use them under deployment environments instead of just general action secrets.
Your mom was wrong, okay? Sharing is not always caring. Please don't share runners between public and private repos, because that's just lateral movement waiting to happen.
When it comes to self-hosted runners, try not to mix continuous integration and continuous delivery.
And finally, only as a defense in depth measure, install EDR on self-hosted runners to catch some more opportunistic attackers.
So another problem here is no one solution is a Band-Aid. If a repository has the more restrictive setting, an attacker could resort to social engineering or wait till a developer has a pull request vulnerability, such as what happened with Intel, and that could end up with the same result. Next, self-hosted runners on public repositories are really the tip of the iceberg. A lot of larger enterprises that use GitHub use self-hosted runner fleets, which have equally bad privilege escalation and lateral movement paths, and a lot of those are just one fish away. Finally, it's important to drive developers to default to fine-grained tokens.
There are 3 things we want every single person here to take away from this talk today and everyone watching online. So if you've been zoning out, focus up, pay attention for this last slide. The first one is that there is a systemic lack of awareness around self-hosted CI/CD agent security in the world's most advanced tech organizations. We've said it before, but it's worth repeating. The number 2 is that attackers are starting to focus on public GitHub repositories to launch these supply chain attacks. And so your public repos should be scrutinized just as much as any externally facing server or asset in your organization. And the third point is, I always like to say ignorance is breach. So a lot of times it's the attack paths you don't know about that get you. This is why we're here today. We want to start raising awareness around these issues. And so devs, defenders, architects, execs, everyone needs to learn about these issues so that they can look at their own systems from the perspective of an attacker, identify the weak points, and then protect their orgs from the next supply chain attack. If you want to start that learning process this week, we are presenting at DEF CON on Saturday. Our talk, Grand Theft Actions, will be more in-depth. So rather than today where we use a lot of case studies, we're going to focus on one case study we didn't talk about today. It's one of our most complex, most impactful attacks to dive deep into the technical TTPs that allow you to take trivial runner RCE and turn them into these supply chain compromises. So this will be a great part 2 to this talk for anyone interested. Come see us at DEF CON if you want to learn more. There's a lot of people we want to thank. A lot of people were involved in this process, but we want to start off by thanking all of the bug bounty triage teams, especially the ones who took these issues seriously, implemented quick remediations, and protected their organizations.
Right, and we'd like to thank everyone who came out here to watch the talk in person and whoever else is tuning in online. And obviously, all of this wouldn't be if it wasn't for the Black Hat organizers for running such an amazing event here in Las Vegas. Obviously, we don't have time for questions, but we'll both be at the breakout room to chat more. Thank you very much.
Thank you.